So for our final lecture, we're going to discuss the theta vacua, which are the quantum vacuum states of Yang-Mills theory. And we'll see that there's a close relation between the theta vacua and the vacuum state of the periodic potential that we looked at yesterday. So throughout today's lecture, we're going to be working in Euclidean signature. And just want to remind you of our notation for Euclidean Yang-Mills. So there's a bunch of -1s and i's compared to what you're used to. So I'm going to choose the generators to be anti-Hermitian, which means they satisfy orientation relation with no I. And there'll be no I in the finite gauge transformation either. Essentially absorb the I into the definition of the generators. That means also that there, if we take a trace of TA, TB, get a minus sign compared to what you're used to. And I'll absorb the coupling into the definition of our gauge fields, so that F mu nu, the usual thing. So our action will have a minus sign if we write it in terms of a trace. That's our notation, just a bunch of i's and -1s compared to usual Minkowski space definitions. Okay, so what our goal today is twofold. So we want to find the vacuum state of Yang-Mills theory, and also discuss. So we'll find that it has a bunch of classical vacua that are separated by a barrier, just like the periodic potential we studied yesterday. And so quantum mechanically, there can be tunneling between the degenerate classical vacua, and the tunneling is controlled by instantons. So we'll find both the classical vacuum states and then discuss the quantum vacuum states, which is controlled by the instanton configurations that you'll construct in the homework. So if we want to study the path integral semi-classically, we should expand around saddle points with finite action. And for S to have finite action, for large R, F mu nu should be order 1 over R cubed, or S, the finite. Now, might expect that tells us that A should be order 1 over R squared. F is related to derivatives of A. But A is a gauge field. So all we really need to impose is that if we want to find an action configuration, is that A should be go like 1 over R squared plus some gauge, or it should be a gauge transformation of a field configuration that is 1 over R squared. So we can add a term here, U du inverse. And we can take U to be order R to the 0. This will still work. So we'll make that choice, which means that, so if U is R to the 0, then U is a function of angles only. So write this as U of x is a function of angles only, where x hat is x U over R. Okay. So finite action is associated with some U that's a function of angles only. But U is not unique. So we perform a gauge transformation on a configuration like this. We get is this, which, if A has this form to begin with, gives us HU du of U inverse H inverse plus something I don't care about. And so we see that with a gauge transformation, we can map U to HU plus maybe some corrections. So if A has this form at infinity, then and we can set HU equal to 1, then we could just remove this term by a gauge transformation. However, this is not possible in general. Because H should be continuous in all of our Euclidean 4 space. So there are maps, so that there are U's that are functions of the angles only at infinity that cannot be mapped into each other by a gauge transformation. And to see why this is possible, why it's not possible to do this, it's useful to consider, instead of a general gauge group in four-dimensional Euclidean space, we can see the same logic applies to U1 in two-dimensional space. The arguments are a bit easier. So let's consider U1 theory in 2D. So in 2D, we want f mu nu to be order 1 over r squared for s to be finite. So a mu be order 1 over r plus u. U inverse. And here again, we want u to be a function of angles only. And take u, so u is just an element of u1, so it's just e to the I alpha of x. So u here is a map from a circle to a circle. So it's a map from a circle in Euclidean 2 space. So there's one angle in Euclidean 2 space that just we can think of as theta that specifies the angle of a circle at infinity. And it's a map, so from the circle at infinity to the group U1, which is just is also a circle. So it's a map from some angle to some element of U1. And the claim is that there are maps of this type that are not continuously deformable into one another. And to see this, we can consider some standard mappings. From S1, S1. So one simple map we can consider is the trivial map, where U, call this U0, theta is just 1. Another map we can write down, call it U1. Theta is just the identity map. And there are also maps that wind nu times. This u nu theta is e to the I nu theta for nu an integer. So this winds around n times because as theta goes from 0 to 2 pi over nu, e to the I nu theta goes from goes around the circle once. So this map goes around the circle once from theta goes from 0 to 2 pi over nu, and again from 2 pi over nu to 4 pi over nu, etc. And so there's a mathematical theorem that says that any map f from S1 to S1 is continuously deformable to one and only one of these maps. And we say that any two maps that can be continuously deformed into one another are homotopous. So this problem can be inverted. So we can find the winding nu, which is the winding number, from a map. Using formula. And it's easy to check that we get the right answer for one of our standard maps, once around a circle n times. So if we just plug in u equals u nu, what we get is that nu is pi over 2 pi integral. We get u nu, we take the derivative, and we just get a minus nu times minus nu. And u times u nu times u minus nu is 1. So i's and minus i's cancel out. The 2 pi cancels with the integral. It works. So from this formula, we can see that under small deformations of the map, this winding number is invariant. So that will tell us then that the winding number can't be changed by continuous deformations of our map. And hence, these news, these standard maps cannot be used in the future. So there are maps that can't be removed by negation transformation. And to see that, we can just continuously deform u plus w. And under deformation, the integrand goes to self plus u d theta inverse And if we vary U inverse, get U inverse U inverse. So right, so the U inverse has U inverse U, U inverse. Okay. And so simplify this. Derivative. So this term will cancel off with the derivative here acts on the last term. That term cancels off, and then we're just left with this d theta acting on the first u and the delta u. So we get u theta inverse du inverse and theta u inverse. Aside from that, these u and u inverse will cancel. And this u and u inverse cancel. So we're just left with u theta u inverse minus, let's write these two terms as d theta of u inverse delta u. So we have what we started with plus a term that's a total derivative that will vanish upon integration. So you can classify the gauge field configurations that have finite action by their winding number. So that's something that's invariant under gauge transformations. So classify all the gauge configurations by winding number. This winding number has some other useful properties. I'll go on with the classification. So, and these sectors are with different winding number will correspond to the discrete minimum that we had in the periodic potential quantum mechanics. So I'll come back to that one, but that's essentially where the discrete set of minimums come from. We divide the gauge field configurations into classes based on winding number. So the winding number, or these maps, we have a map that's the product of the maps. And the winding number of U is just the sum of the winding numbers of U1 and U2. And to see this, we can just deform U1 so that it's the identity on half of the circle, and U2 is the identity on the other half of the circle. And then if we wanted to calculate U of theta using this formula, it would just divide into two pieces where we sum the winding number on half of the circle, we would get the winding number for U1, and the other half would get the winding number. So this will be useful because the instantons will let us change the winding number. So we'll have the analogy with the quantum mechanical periodic potential. We have a discrete set of minima that are characterized by the winding number, and instantons will be change the winding number by this property. So one other useful form we can write. The winding number. Okay. And so this U, D, beta U is basically just one component of the gauge field. So we were considering a mu to be U inverse at infinity. So that tells us that we can write this in terms of the A theta component. And, well, write this in another way. I'll also write this. In terms of a radial unit vector here. And epsilon in one component. Gauge field. Then Gauss's theorem tells us that we can write this as an integral over all of Euclidean Q space instead of just a circle on the boundary. D mu. So we're in Euclidean space, so upstairs and downstairs in Q's. But this is just nothing but right. This in terms of the field strength, and we get a familiar expression. So this was our formula for the axial anomaly. So these anomalies and instantons have a connection that you'll explore a little bit in your homework. So, what have we seen so far? So far we've just been looking at the U1 model in 2 dimensions. And we have seen that we can classify gauge field configurations of finite action by winding number. And this winding number is homotopic invariant, which means it's invariant under continuous deformations. And everything I've said about U1, U1 gauge theory in 2D has very close analogs in for SU2 in 4D. So for SU2 and 4D, we can write a element of SU2 in the usual way, as e to the minus I lambda times the Pauli matrices over 2, where lambda is just some real parameters. But since the Pauli matrices all squared for the identity, and product of any two of them can be written in terms of the third one, we can also every term in this exponential is just going to be proportional to either the identity matrix or one of the Pauli matrices. So we can write this as A plus IP sigma. Where A and B are real parameters. And if this is unitary, then we have U dagger U is 1, which tells us that A squared plus B dot B is 1, which is precisely the equation for a 3-sphere. So SU2 is equivalent to 3-sphere. And so in 2 dimensions for U1, we wanted to look at maps from S1 to S1, circle to circle. For SU2 and 4D, what we want to look at are the homotopy classes. Of maps from 3-sphere, so at spatial infinity for 4D to the 3-sphere. So this is the 3-sphere at R is infinity, and this is and like in the U1 case, there are a set of standard maps. So we take U nu of x b at the x hat plus I x hat dot sigma in nu. Or again, x nu is at nu is x nu over r, and r squared is just the linear radius. Then it can be shown that, and just like before, we have that any f from S3 is homotopic to 1 and only 1. Unit. And so there's a formula for the YD number. These maps. Rewritten this is the integral of trace epsilon k u dot inverse j inverse k inverse. So basically the same arguments that we made before applies. So we can go through very similar derivation to show that this winding number is invariant under small perturbations, under small continuous deformations. So it's a derivation that works similarly to this one. There's more terms because there's three factors of U universe. It's slightly lengthier, and I'll go through it. It works very similarly. So that almost the same argument shows us that this is an invariant, and you can plug in this expression for the U nus into this formula to see that you do in fact get nus. So there are a countably infinite set of homotopy classes of maps from S3 to S3. You can also show that this, again using a similar argument to what I just showed here, that this can be written in terms of field strength. And the expression depth is this one. And so, again, this expression should look familiar to you. This was the formula we've gone for the anomaly. Explore a little bit of connection. So we're ultimately interested in Yang-Mills theory in 4 dimensions. But we might be interested in other groups besides our gauge theories in 4 dimensions. We might be interested in other groups besides SU2. So let's consider the other cases. So for U1, 4D, there is no winding number. And every map on S3, S1, it's a formable to the trivial map. If you try to construct a non-trivial mapping, you can see too much effort that it always has to be continuously conformable to the identity. There's no way to graph a 3-sphere or even a 2-sphere circle. Okay. What about other groups? So for G, a simple Lie group, simple non-abelian Lie group. There is a theorem by Glass that says that any map 3-sphere G can be continuously deformed into a mapping into a SU2 subgroup. So really there's only two cases. There's U1, which has no non-trivial maps, and everything else is the same as the SU2. So what does all this imply about the vacuum of Yang-Mills theory? So like the periodic potential from yesterday, Yang-Mills theory has multiple minima. And to see this, let's consider two different gauge field configurations. We can look at gauge field configuration A nu1, which is just U of nu1 d mu U of nu1, and A mu 2 is U u2 U u2. So both of these gauge field configurations are gauge transformations of 0. And hence have vanishing field strength. Which means that they'll have zero energy. So we can compute the Hamiltonian for Yang-Mills theory, gauge A0 equals 0, and just be it'll be 0 if the field strength vanishes. But we've just seen that U nu1 and U nu2 cannot be deformed into one another. So that means if we want to find a gauge field configuration that interpolates between these two gauge field configurations, the interpolating field will have to be of a different form. It won't be pure gauge, and it'll be non-vanishing field strength and hence non-vanishing energy. So there's an energy barrier between these two configurations.
As I think there should be a minus sign at the definition for the A mu un.
A minus sign where?
And the u under the bracket.
Yes, thank you. Okay, so we've seen, so we now have an argument that the analogy with periodic potential is very, very close. So we've got a comfortably infinite set of degenerates, classical vacua, that have a very big thing, just like the periodic potential we studied yesterday. And so that means that there will be a discrete set of vacuum states. N, where N labels the winding number of the gauge field configuration. And there'll be instantons that mediate tunneling between these states of definite winding. And in your homework, you're going to construct the instanton that does that. And what you'll show is that there is an instanton with finite action S1 8 pi squared G squared that changes the winding number of it. So the analogy between Yang-Mills theory and the periodic potential we studied yesterday, we now have basically all of the same ingredient. We've got a countably infinite set of vacuum states, have a instanton that mediates tunneling, moves us from one of the degenerate ground states to the next one. And so the analogy is very, very, very close.
And from the Yang-Mills point of view, where do we convince ourselves that this won't be a perturbative process?
That it won't be a perturbative process? Well, so there are several ways we can see that. One is that these are homotopy classes. The winding numbers characterize divide the theory into sectors.
Okay.
And any small perturbation, if we do continuous information around that, one field configuration in one homotopy class will remain in that class.
Okay.
We're really dealing with large fluctuations that take us from one class to another. So these are invisible imperturbation here. And, well, so the instanton, or we can think about instantons as saddle points for the inaction. And the effects of these non-trivial saddle points are always exponential in 1 over h bar. So they disappear, they're invisible. And so since we have an instant time, we expect that this matrix element should be proportional to e to the minus n minus n s1, where s1 is the action of the instant time that changes the winding number by 1, which tells us that the states with definite winding number are not eigenstates. Now done. In basically the same way as the periodic potential displacement. And so the eigenstates are the so-called theta vacuum, which are linear combinations of the states of definite winding number. So these are the energy eigenstates. And we can see this by using n prime h theta, which is sum over n minus I n theta n prime h n, which also write as minus I n theta minus n y minus n plus 1. And now if we shift our index of summation n to m plus n prime, write this as sum over m to minus I m plus n prime theta minus m plus 1. And write this then as e to the minus I theta sum over m minus I m theta to the minus m plus 1. And this here is just the overlap of n prime theta. And this is the energy the energy for any n prime. So we see that these are the energy eigenstates, and these are the so-called theta vacuum. So what does this parameter theta mean? Last few minutes of just plugging stats. Briefly at the interpretation of this theta. So one question we can ask is, what's the we start in some theta vacuum. What's the amplitude to go to different theta vacuum after some Euclidean vacuum? And so we can write this just using the definition of the eta vacua as a sum of over n and m of n e minus h m I and theta prime and it's m theta. And find nu to be n minus m. Write this as the sum over n. E I n theta prime minus theta. Sum over nu times a path integral over gauge fields with winding number nu. I theta nu minus S of n.
These were the zero energy fields.
So these are all configurations with winding number. So what's left to do this is, so if we want to transition from a state with winding number m to a state with winding number n, the only possible way to do that is there to be gauge field in between as winding number j. Change the winding number by n minus n. So the winding numbers are added. So this is we're doing a restricted path integral of this over some subset of the configurations. So the only ones that will contribute. This factor out front is just proportional to a delta function, theta minus theta prime. As we might expect, these are energy eigenstates with different energies. We're not going to transitions between the two. And over here, we've got a sum over all possible winding numbers, so we can rewrite this as path integral over all field configurations times e to the minus s. But now we have a new term in the path integral. We have e to the I and I nu theta, which can be written in terms of the field strength. As shown in this formula. So we get an extra term, right, that's this. And so this is a new term that we essentially we could add to our original action. And this is a gauge invariance, Lorentz invariance, renormalizable term that we could have started out with when we first ran into Daniel's theory in 52. The reason we didn't consider it is it's a total derivative, but we've seen if we're going to do non-perturbative physics, this term has to be there. And one important consequence of this term is that it violates both parity and CP. So B and T. This term and can have observable consequences. So, which I won't have time to discuss in more detail, but there's particularly strong constraints on terms of this form for QCD. And experimentally, the theta angle for QCD is less than about 10 to the minus 1. Principle could be there. Observationally, we haven't seen any effects of it yet. We know it's very small. And why that is still a mystery. All right, so essentially out of time, but we've gone through a very brief introduction to both anomalies and instantons. There's a lot more in both of these subjects that covered due to the lack of time, but I hope this gives you some idea for the basic ideas behind anomalies and instantons and a few of their uses.